Central limit theorem. The central limit theorem states, regardless of the distribution or shape of the population, the distribution of the sample means is approximately normal if the sample size is sufficiently large. This approximation improves as the sample size increases. The sample size required will depend on the underlying population. The more normal the population looks like to begin with, the smaller the sample size we'll need before we start to see results. In fact, the sample mean has a normal distribution for all sample sizes if the population is itself normal. The central limit theorem has two properties. The first one states that the mean of the sample means is equal to the population mean. The second property states that the standard deviation of the sample means is equal to the standard deviation of the population divided by the square root of the sample size. Here we call the standard deviation of the sample mean as the standard error. Now, since x bar is normally distributed, we can convert it to z. The formula that accomplishes this is z equals x bar minus mu divided by sigma over the square root of n.
The weight of pennies minted after 1982 are normally distributed with mean 2.46 grams and standard deviation of 0.02 grams. What is the probability that in a simple random sample of 10 pennies minted after 1982, we obtain a sample mean of at least 2.465 grams? I first start off by listing our variables. We have that the mean is 2.46 grams. We have the standard deviation is 0.02 grams. We have a simple random sample of 10 pennies, so n is 10. We want to find the probability that the sample mean is at least 2.465 grams. So the question wants us to find the probability that x bar is at least 2.465 grams. Now, what we need to do is convert this x bar into a z. According to the central limit theorem, we have z is equal to x bar minus mu divided by sigma over the square root of n. So the idea is to convert this x bar into a z-score so we can use our table. So z is equal to, and I'm going to plug in the values for x bar, which is 2.465. I'm going to subtract the mean, which is 2.46. And I'm going to divide that by the square root, or actually the standard deviation, which is 0.02, divided by the square root of n, which is 10. Now, when I type this in a calculator, I want to make sure that put parentheses on the numerator and parentheses on the denominator, so the calculator will give us the correct output. Parentheses first, then 2.465 minus 2.46, close off the parentheses, divide, open the parentheses, 0.02, divide, then we're going to press the square root of 10, close off the parentheses for the square root, and then close it off again for the denominator. And we're going to round this to 2 decimal places. So z is equal to 0.79. And now, instead of finding the probability that x bar is greater than or equal to 2.465, we have changed the problem now to finding the probability that z is at least 0.79. Now, if you look at this carefully, this is the area to the right. So I need to use my z table to find the value of the area to the left of this, then subtract it from 1. I locate 0.7, and on the column side, we locate 0.09. If we intersect the row and column, we get the area that we're looking for, which is 0.7852. We're going to subtract from 1. And this gives us 0.2148. In order to do example 1 on Statcrunch, we have to go to Stat, Calculators, then Normal. So Stats, Calculators, Normal. I know the mean is going to be 2.46. And now the standard deviation is going to be 0.02, but we have to use the central limit theorem in this problem. So I'm going to put divide by SQRT, and I'm going to put a set of parentheses around 10. Okay, so again, for the standard deviation, I'm going to use 0.02 divide by the square root of 10. Make sure you put the parentheses around the 10. Now we want to find the probability that the sample mean is at least 2.465. So we're going to type in 2.465 and then compute. And we get about the same answer. Example 2. Suppose the mean time for an oil change at 10-minute oil change joint is 11.4 minutes with a standard deviation of 3.2 minutes. If a random sample of 35 oil changes is selected, describe the sampling distribution of the sample mean. B. If a random sample of 35 oil changes is selected, what is the probability that the mean oil change time is less than 11 minutes? In part A, we want to find the shape of the sampling distribution. So according to the central limit theorem, the sampling distribution is approximately normal. Now the mean is 11.4 minutes, and the standard deviation of the sampling mean by the central limit theorem is 3.2 divided by the square root of 35. In part B, we're asked to find the probability that if we select 35 oil changes, that the mean will be less than 11 minutes. So we want to find the probability that X bar is less than 11 minutes. Now we have to convert this X bar to a Z score. We need to use the formula Z equals X bar minus mu divided by sigma over the square root of n. X bar is going to be 11. The mean, according to the problem, is 11.4 minutes. The standard deviation is 3.2 minutes. N is 35. And we need to plug everything into this formula now. Z is equal to 11 minus 11.4 divided by 3.2 over the square root of 35. So our Z is negative 0.74. Now, instead of finding the probability that the sample mean is less than 11, we're now asked to find the probability that Z is less than negative 0.74. So we'll use our Z table to find the area on the left. Negative 0.7, and the column is going to be 0.04. And this gives us an area of 0.2296. So from our Z table, we have our final solution is 0.2296. So if we select a random sample of 35 oil changes, the probability that the average of those 35 will be less than 11 minutes is about 22.96%.